Today we are going to learn about the concept of the random variable. The concept name is the random variable. So this is the second unit of your syllabus. So the name of the unit is random variable. Random variable. Okay. So coming to the definition of random variable. Definition of the random variable. It is a function. A random variable is a function. Function. Function which maps all the elements of all the elements of sample space all the elements of sample space into a real axis to a real axis. This is the definition of a random variable. So it is represented by a capital letter. It is represented by a capital letter. Always represented by a capital letter, by capital letter, that is capital X, might be capital Y or capital Z, etc. So that means your random variable must be always representation in terms of only capital letters only. So now I am moving on to the example of random variable. How it is represented? How in the figure manner. So suppose I am considering an experiment. An experiment. So if you want to know the sample space, you should do one experiment. So that experiment might be anything. So what I am doing is I am rolling a die. I am rolling a die and a coin together. Rolling a die and a coin together. So what is the sample space here? I am getting here sample space here. So since die has 6 faces, coin has 2 outcomes. So totally I'll get 6 into 2. Totally 12 outcomes in my experiment. So that means so the sample space is equal to, the sample space might be represented like this, s equal to totally there are how many? 12. That means T1, T2, T3, T4, T5, T6. Similarly, here H1, H2, H3, H4, H5, and H6. So this is called the sample space. So to find the, to note the random variable, first you should now find out the sample space of the given experiment. So from the given experiment, we can say that this is the sample space. So now according to the definition, it is a function. So that means it is a function. Function is some. It is in terms of, if you see in your previous classes, your function is represented by like this, f of x, like that. So here also our random variable is, it is capital X, and it is represented by in terms of your sample space. So the sample space, the random variable is sample space is represented by what? X of s. So you should take a function. You should take a function. This is x of s. X of s. Suppose I am assuming x of s equal to I will take x of s equal to 1. 1. I will define here. X of s equal to 1 if 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 uh, point faces t, minus 1 if it is h. So that means the coin faces tail, I will take the value as 1. If the coin take coin faces head, I will take the value of minus 1. So now see, so this is my real axis. So real axis means it starts at 0, 1, 2, 3, 4, 5, similarly minus 1, minus 2, minus 3, and so on. So this is the real axis. So what the random variable said means, it maps all the elements of sample space, into real axis. Now see, I'm mapping the real axis, sample space. So here you will get, see here you will get all the heads, you see here you will get all the heads, the sun, all the heads. the right side. So if ever I am getting head, so if it is occurring, the value should be what? Value should be what? 1. So the mapping is done when the head is there. Similarly, if tail is coming, what is my value? What I am define? Sorry. Okay. So take here head comes 1, and if tail comes -1. Whatever it may be, you can define any number of ways. So but for timing I am defining like this: x of s equal to -1 if t faces, x of s equal to 1 if h faces, point faces h. So now here there are six number of outcomes which are facing h. I mean that means head. So that's why I am mapping this head possibilities into real axis through my function. So what is my function here? My function is here. This is this x of s. So you should map your sample space through random variable only. Then only it is valid. Okay. There should be a mediator that is called this one. This is a random variable. This is a random variable. Through that you should map. You should map. Now similarly, I'll say what I will do is here I'll map tail. So what tail says here? If tail comes, it becomes what? -1. So -1 means, so for that whatever may be the value, for all these values, what I will get? I get -1. So the entire figure, this entire figure is called random variable. Random variable representation in terms of figure. So here what you will get? You will get sample space, you will get random variable function, you will get what? The real axis. The real axis. And one more thing, this is not one. You can assume this is just x of s. This is just x of s. Okay. And my function comes like this. And I am doing x of s on the outside of your function, outside of the random variable. So this is one example how to represent a random variable. Now see, there are different types of random variables. There are different types of random variables. So there are those are see here. Types of random variables. Types. Types of types of random variables. So the first one is continuous random variable. Continuous random variable. Second one is discrete random variable. Discrete random variable. The third one is mixed random variable. Mixed random variable. So there are three types of random variables: continuous, discrete, and mixed random variable. So as the name comes, continuous, discrete, mixed. So continuous means they should be see if you move upwards, So here if you see this one here, in the real axis you are having only 2 points. Only 2 points. If you see -1 and +1. So in this case, this random variable is called discrete random variable. Why? Because here only discrete values, 1 and -1 is there only. There is no other values. So 1 and -1 is there. That's why it is called discrete random variable. So if I want to call this one as continuous random variable, that means we should have your arrow mark should indicate everything from 0 to 1, everything from 0 to 1. But here we are mapping to only 1. Here it is mapping to only -1. So the mapping onto the real axis completely depends on your function and also on sample space. So based on the sample space and based on the given function, random variable function, you can determine whether the given random variable is continuous or discrete. Continuous or discrete. Now, continuous random variable, how it is defined, how it is looks like, you can see here. Continuous random variable. So, for continuous random variable, there should be one sample space, there should be one function x of s, and there should be one real axis x. So for every random variable there should be like that. But what is the change you have to see here is for continuous random variable. So if it is a discrete sample space, discrete means you will get 1, 2, 3, something like that, discrete. And if you define your x of s equal to s like that, s like that. That means On the real axis you will get what? S means you have S means 1 2 3 on real axis. From sample space you'll get 1, you'll get you'll get 2, on another one it is 3, 1 2 3. So what is the whatever value is showing in the sample space, that should reflect in your real axis. But this is called discrete sample space, sorry, discrete random variable. Why? Because here the values are discrete on the real axis, so you should consider the first real axis itself. So the values of real axis must be continuous. So for that purpose, so you should define sample space in a continuous manner. So I will see like this. So I will take the sample space of our continuous random variable is like a clock, or a circle having values from 1 to 1 to suppose from here 12, like this. So 1 to 12, and my needle is slowly moves like this. Suppose here it is 2, here it is 3, here it is 4, 5, 6, 7, 8, 9, 10, 11. So now see what happened here is what will happen here is your this needle is slowly moves, but does not move directly from 1 to 2. That means if it is moved slowly, there is a chance of getting over one infinity values between 1 to 2. Why? Because this needle is not discrete, this is continuously slowly moving like this. That means the here what will happen is the sample space, if you define the sample space here, it might be your sample space might be in the range of 1 less than or equal to s less than or equal to 12. That means the needle might stop in between 1 and 12 on anywhere from 1 to 12. On anywhere it might stop. So that you should understand, that we should understand. So the sample space here is 1 to 12, 1 to 12. Okay. So if now if I say that x x of s equal to s, so I am assuming my x of s equal to s. Now see, x of s have infinite values, s have infinite values. Now what I have to do, I have to map all the values of s into real axis. So that means your shape, it will be coming like this, and it will comes every point in your sample space, every point in your real axis. So, and it is showing that it extends until infinite. That means every point on your sample space, here it is mapped, here it is mapped. So, and we can say that the values are continuous. Why? Because here you will get at 0 1 0, you will get at 0.1, you will get at 0 point everywhere between 0 to 1, 1 to 2, 2 to 3. Why? Because I am I am defining my random variable like this, x of s equal to x of s equal to s. So there are number of possibilities for needle, number of possibilities. This needle, this pendulum, like that, anyway you can call. So this needle stop, so it can be stopped from 1 to 2 on anywhere. That means it is having infinite values, and everywhere it can stop. That means the total number of possibilities of outcome sample space is equal to infinite. So that's why I'm assuming my s equal to like this, sample space is equal to 1 less than or equal to s less than or equal to 12. So in this range it will having. Now I am defining my x of s is like this, x of s equal to yes, like same as sample space. So if you see here, so the sample space is continuous. So in the same way, we are defining x of s equal to s. To map the all the elements of sample space into real axis, I need 0 to infinity points, infinity points. So in that way, I can say that this is a continuous random variable. So the condition for here is continuous random variable is the sample space must be continuous. First conditional must and should be sample space must be continuous. That you should remember. Sample space must be always continuous for a continuous random variable. So the second one is discrete random variable. The second one is discrete random variable. So we have already seen the example of discrete random variable already. So I'm again going to explain. So this is the example of discrete random variable. This is the example, exact example of discrete random variable. Why it is the random variable name always depends on the number of points on your real axis, that you should remember. If number of points on the real axis is infinite, then it is called continuous random variable. The number of points are finite, then it is called discrete random variable. Now see, here already we have defined sample space. So it is having total number of 12, 12 outcomes, and I am defining x of s equal to minus 1 if coin faces tail, and if it is 1 if coin faces head. So for all the values of tail, I'll get minus 1. For all the values of h, I'll get plus 1. So here I am having only two values on my real axis. So I can say that this is a discrete random variable. So that is the example of discrete random variable. Now moving on to the third one. The third one is mixed random variable. Mixed random variable. As the name indicates mixed, your real axis, our real axis must have continuous as well as discrete values. Continuous as well as discrete values. Now see, in the same way, I am taking my sample space is from the needle, and my x of s is like this. Okay, so I am defining, so here we already defined it is 1 2 3 like that. So I am defining my x of s equal to, sorry, first define s. So s is from 1 less than or equal to s less than or equal to 1. So sample space, this needle starts on anywhere from 1 to 12. This is the meaning of this one. And I will define x of s like this. X of s equal like this. X of s equal to 1 for for if 1 for if it is showing 1 less than or equal to 1 less than or equal to s less than or equal to 6. That means if your sample space in between 1 to 6, you can say the value is directly 1. And if I am saying it is yes, if s for 6 less than s less than or equal to 12, s less than or equal to 7. So from this, if you define the random variable, random variable like this from the sample space, if you draw the mixed random variable, it is like this. So whatever the value from 1 to 6, from 1 to 6, that for that I have what the value is, the value is 1. The value is 1. So we can get values from 1 to 6 from here. So if the needle is here, is in this range, is from here to here, the needle is from here to here, I can say in that case the random variable, the sample space maps to point 1, maps to point 1. So and the point should always comes through random variable only, it does not comes out. So this is the first case. Similarly, I can say x of s equal to s for 6 less than or equal to s less than or equal to 12. That means if your needle in this space, that means 6, here it is 12. So in this space, what I will do? I want value of s. That means if it is at 6, if it is at 6.1, it is 6.1. It is 6.1. Suppose I am writing this one as 6. 6.1. If it is a 6.2, 6.2, 6.3, 6.3, that means here you will get number of values on the from 6 to 12. Number of values from 6 to 12. Okay, so this is my small x. So here if you see from 6 to 12, it is in the continuous form. It is in the continuous form. Why? Because number of values will be coming. And whereas from 1 to 6 you are having only one value, so if you see it, this one value is called discrete value, and from 6 to 12 these are called continuous values. So if the real axis contains continuous as well as discrete values, in that case The random variable is called mixed random variable. Mixed random variable. I am telling you again. If the uh, real axis contains, if the real axis contains, so one more thing, and your mapping always starts goes through your random variable only. Random variable only should not comes outside. Now see, so it comes all through function, and here it is having continuous values and it is one discrete value. So the real axis has both continuous and discrete values. So that's why the random variable name comes the name here comes the name as mixed random variable. So this is what about random variable concept. So this random variable concept is very important for your exams. So they gave you a question like that, explain about random variable concept. So in that case you should write definition of the random variable, and you should explain each type of random variable, three types of random variables with example. So that is what about random variable concept. Now the next one is to it might be small question. Conditions for a function to be a random variable. Condition for a function to be a random variable. Okay. So there are two conditions. There are two conditions. So these are, so the set x less than or equal to x is must be an event in the sample space. In the sample space. Sample space. So these are the first condition, and the second condition is the probabilities at x equal to minus infinity, and the probability at x equal to infinity must be 0 for a function to be a random variable. So these are the conditions. Two conditions should satisfy a function for a function to be a random variable. This might be given for 2 marks question. So see this one. So the set x less than or equal to x is must be an event in the sample space, and b, and the probability of x equal to infinity and x equal to minus infinity must be always equal to 0. These are the two conditions for a function to be random variable. So now the next concept is probability probability distribution function. Distribution function. Probability distribution function. It is sometimes it is called letters, capital letters PDF, or sometimes it can be represented like this: capital Fx subscript C. How it is represented? Capital F subscript capital X of small x. So this representation is very important. See here represented. So the definition of probability distribution is like this: the probability of an event, the probability probability of an event. So for every event there should be one probability. So that is the probability of an event. The probability of an event, the event is x less than or equal to x. X less than or equal to x is called is called is called PDF. So that means probability distribution function. So the definition is like this: the probability of an event x less than or equal to x is called probability distribution function, and it is represented by is represented by what? It is represented by f capital F subscript capital X of surface. So now mathematically, the probability distribution can be represented like this. Can be drawn. I mean, can be write like this: f x of x is equal to. So probability distribution function is equal to probability of an event what f less than or equal to f less than or equal to. So this is the very important definition in your probability. So you should remember this definition compulsorily. So you can ask this. There may be chance to ask to give this definition for very small questions. Okay. So this is the definition. Now moving on to the properties. Moving on to the properties of probability distribution function. Moving on to the properties of probability distribution function. So the first property is so fx of minus infinity, sorry, plus infinity, I write plus infinity. Fx of minus infinity is always equal to 0. The first property of your probability distribution function is fx of minus infinity is equal to 0. The second property is fx of infinity is equal to 0. Fx of infinity is equal to 0. So I will explain later these properties with examples. So first see this one. Fx of minus infinity is equal to 0 and fx of infinity, sorry, not equal to 0, is equal to 1. And the third one is p of x1 less than x less than x2 is equal to fx of x2 minus fx of x, fx of x2 minus fx of x1. This is the third property. So if the random variable is in between two values, two numbers, you can call between two numbers, then in that case the random variable, the probability is fx of x2 upper number minus lower number. That means fx of x2 minus fx of x1. So fourth one, fourth one, fx of x1 less than fx of x2 if x1 less than x2. If x1 less than x2, what you will get? Fx of x1 is always less than or equal to fx of x2. Now the fifth one is random variable. It is always lies between 0 and 1. Why? Because you see, because you can already say that this is a probability. So probability distribution is nothing but probability. So that means your probability is always must and should lies between what? 0 and 1. 0 and 1. So this is the fifth property. And the last property is sixth one. Sixth one. So fx of x plus is equal to fx of x. Fx of x plus is equal to fx of x. That means the distribution function is a right continuous function. Right continuous function. These are six properties. Now see, we will see one more time the properties. So fx of minus infinity is equal to 0. So minus infinity, that means leftmost point on your real axis has a probability of 0. Similarly, fx of infinity is equal to 1. That means rightmost point has the probability of 1. Similarly, third one, p of x1 less than x less than x2 equal to fx of x2 minus fx of x1. So that means in the range, in some range, if you want to find the probability, you can say that is the difference. That is the difference. And if fx of x1 less than fx of x2, if and only if what the denominator inside function, inside numbers must be less than, there must be having relation x1 less than x2. And if the fifth one is, so the random here probability distribution function is a probability, right? So that's why it is always right, lies between 0 and 1. And the sixth one is the probability distribution function is a right continuous function. Right continuous function. So these are the probabilities of, these are the basic introduction about the probability distribution function, how it is represented, and the properties, their six properties, so we have seen continuous. This is continuous probability distribution function. So in it is also there is discrete in that for the, it is for the continuous random variable. So for discrete random variable also there is a probability distribution function. There is a probability distribution function. So for a discrete random variable, the probability distribution function is also represented by like this, but with summation. It is sigma I equal to 1 to n p of x equal to xi into u of x minus xi, u of x minus xi. So this is the probability distribution for a discrete random variable. So we see for a continuous random variable we will get integrals, whereas for a discrete one the operations are completely on summation. So for that purpose here it is as the name indicates discrete, fx of x is equal to sigma e equal to 1 to n, p of x equal to xi, u of x minus xy. So what is meant by u here, where u is what, u means u of x minus xi, u means what, so u means it is a step function. Okay, and the definition of step function we already know, u of x equal to 1 for x greater than or equal to 0, 0 elsewhere, 0 elsewhere. So this is the definition of discrete random variable probability distribution function. So this concept is also very important. Explain probability distribution function. Like that, they will give you formula. I mean problem. I mean they will give you a question. In that case, you will write definition. In that case, you will write definition. You have to write properties. You have to write properties, and then you have to write the probability distribution for discrete random variable also. Discrete random variable also. So the discrete random variable fx of x equal to sigma equal to 1 to n, p of x equal to xi into u of x minus xi, where u is the step function and it is defined like this.